So good morning again. I'm Olivier Santies. I'm from INRIA and University of Rennes. I'm happy to chair the session and be the timekeeper for this session. So we will have a very interesting talk, I assume, on safety, security, verification of security, and different flavors of software and also hardware today. So that's very interesting. So the first talk is from Edward Wilford, who is a senior research director in Automotive at Wards Intelligence and Omdia Automotive. Please welcome.
It's great to be back at the RISC-V Europe Summit. When I came last year, I was finishing up my time as an IoT analyst. And back then, one of the things I used to talk about all the time is that automotive isn't special. Then I took over automotive, and the funniest thing happened. Completely changed my mind on that. And for the last year, I'm saying automotive is special. But no, I've come around on it. And I think what unites automotive and industrial in particular is much more important than the distinctions we make, the differences we draw on it. The line between automotive and the other segments, is becoming blurred. And this is particularly related to the growth of significant amounts of compute. Slides going? There we go. Intelligence, being added to automotive, as well as a shift in requirements that had previously been thought of as sort of specific to automotive, namely safety, spreading to other applications. Now, this mostly boils down to, again, between automotive and industrial. They're the two closest, but in general, I really want to start thinking about applications in a different way. We have what I call our bowerbird tendencies as analysts. Bowerbirds sort things, like pebbles, in a particular way. Sometimes it's by color, sometimes it's by size, sometimes by shape, and once they have their piles, those are the piles they have. Right? They're not going to think about them in a different way. And sometimes we need to shuffle those piles up. And it's so hard to do. It's so hard to have things organized in one way and then change the concepts of how you organize them. But we need to go back to first principles sometimes, because we make distinctions without differences sometimes. We need different kinds of piles sometimes. And we should be looking at things more by function and deployment type rather than by vertical, because a theme I come back to again and again is that the box doesn't care. The chip does not care if it's in a car or if it's in an industrial robot or an automated kiosk or a smart camera. It needs to know, how safe do I need to be? What embedded intelligence is being deployed? What intelligence is being deployed in the cloud? How connected am I and to what? And those are the fundamental considerations for a lot of those items. I talk about overlays, particularly for IoT and industrial. So there's embedded, and there's embedded connected, and secure embedded connected, and safe, secure, embedded connected, and accelerated, safe, secure, embedded connected, and any variations on those. That is what fundamentally matters. That is what I think what is interesting. Safe and secure should be in the same breath, and for about half this room is the same word, but that's a conversation for a completely different conference. Historically, automotive has been a sandbox. It's a nice enclosed space. You are not allowed to enter if you're on the outside, and time itself literally runs differently inside that sandbox. Incredibly long development cycles historically. 4 or 5 years, not uncommon. Unique requirements, including safety. But what is really unique about it? Occupant safety, yes, we can see that is unique to automotive. A very complex tier system. The OEMs, the tier 1s, the tier 2s, and now the tier 1.5s, and who supplies them, and the barrier entry has always historically been extremely high. And part of this extreme resistance to change in automotive is that some of these org charts, in Western OEMs in particular, are 100 years old, and written on vellum. And there's laws against changing some of these divisions. You can still map a lot of company structure by taking a car apart and looking at the ECUs. And you can figure, oh yes, there's definitely a senior vice president for this. You can tell, just by looking at that controller type. The closest analog to all of this is industrial, which has had very long development times, not as long. A comparatively closed ecosystem, like automotive, is space dominated at one end by a few massive players. That can also be applied to a lot of other segments, data center, consumer. You see these same things coming up over and over again. It's not enough to say automotive needs to be treated very, very differently. Automotive needs to have its own safe space off to one side. A lot of things that industrial and automotive have in common, some of the same players. I mean, Bosch, for example, is dominant in both industries, and for a good reason. So we see some of the basic differences between traditional auto and industrial semis in particular. Well, we've discussed some of this. We'll pick up the rest of this later on. It's not a million miles apart, these two. Okay? If you're trying to differentiate them, that little box on the right is how you would do it. And one thing which is actually bringing them together is SDV. And I say SDV, I'm actually trying to push people inside my team to talking about software-defined architectures or software-defined systems. Because whether the software is defining a vehicle or not is a case of deployment, okay? Box doesn't care. Explosive market with software-defined vehicles. Everyone is looking into this to some degree, some more, some less. Some are way ahead. Tesla, for example, the upstart Chinese EVs are way ahead of everyone else, but everyone is looking at this. Volkswagen, one of the largest investments in software-defined vehicles. GM looking very heavily at this. Significant correlation with EV platforms, but sometimes we talk about SDVs and EVs in the same space, and that's not necessarily true. BYD is extensively investing in software-defined vehicles for the ICE space. Some people look at their hybrid platforms, defining them by software. You don't need an EV to have software-defined vehicles. Omdia expects OEM and software digital investments to triple by 2035. Okay, and that's what's going in. That's your 10 years. It's a pretty sizable figure. Recent Omdia survey, 75% of OEM respondents expect software definition to be a core feature of almost all their new models by 2035. Okay. So they're betting a lot on this. And no matter how much they're compacting their design cycles, that's a lot to get done in 10 years. How much and how defined is another question. Maita Becerra from my team is our main SDV analyst. And one of the things she looks at is, like ADAS levels, there's a tendency to think of it as stair steps, right? Like you go from level 1 to level 2 to level 2 plus to level 3. And with software-defined vehicles as well, like not everyone's going to the same place. Not everyone's got the same journey. Not everyone's going at the same speed. So people will have some of their vehicle defined by software. Some will have all of it. Just like some people are aiming for level 5 and some are happy at level 2 and some are going for level 4. It's not a progression, right? It's not a march. Okay? There's no tape to cross and there's no software-defined medal hanging over your neck when you reach the end of it. Hardware dependent. These control units each have their own specific hardware, and that hardware would have software specific to the application that it was running. Okay? There's no sense of a unified structure to that car. The software was put in as it was needed. Now we're looking more at a platform, okay? A whole integrated software platform that is a complete revolution, and I genuinely mean this, in how we think of the car and what constitutes the car. We are pivoting to predictive maintenance and onboard AI diagnostics and incredibly cool things that you can do, right? We don't just define things by software for the sake of it. We do it because it expands what we can do with the vehicle. Okay? The more that a computer can see the whole car natively, the more we're going to say, well, let's use AI to fix things. Let's use AI to make the car last longer, to run better, to improve it over its lifespan. This chart shows our Omdia forecast for SDV sales on centralized domain architecture by type of OEM. And you can see that the incumbents are catching up a bit. Okay? That growth, the disruptors are a big hump out there, but the incumbents are starting. That shows the level of investment. And this is truly a transformational shift. Okay? This isn't just a few people going off on their own in a maverick way and will be corralled back in later. The whole industry is truly committed to this. In practical terms, what are we talking about when we say the shift from distributed to software-defined vehicles? Historically, these cars had anywhere between 30 and 150 ECUs, electronic control units. Like some vehicles had as many as 200, I understand. That is a huge amount of distributed compute, a huge amount of things that can go wrong, and there's a minimum of 20 of those on any car that will take it off the road. Consolidated EE architecture, typically between 1 and 6 centralized domains. So if you're combining these ECUs, if you're taking up to 200 control units and putting all that compute, focusing it on a few elements, okay, you can put high-performance compute in there. Okay? You can get stuff from that. You can balance, you can offload, you can use that compute where and when and how you need it. Hardware and software decoupled, so greater flexibility. You can choose which software package you want to add on. Ethernet connectivity, it's a huge thing. Speeding up communication between control units and sensors, getting that miles and miles of copper wire out of there and replacing it with something like Ethernet, giving you the flexibility and the speed. Seamless connection of ecosystem devices to the cloud. And this cloud-to-car connectivity is a huge part of software-defined vehicles. Like OTA is essential to it. Constantly updating it is essential to it. And building that connectivity in from the point of manufacture is going to be hugely important. I'll skip through some of the SPV stuff because it's basically sort of generally what you get when you take a lot of controllers and put them into a big compute box instead. Why are we talking about software-defined vehicles and software-defined systems, software-defined architectures in the same systems? So, traditionally, in both automotive and industrial, we start with fixed function hardware. Okay, limited updates. You have to take the thing to the shop and plug it in, to fix it. Okay. Completely separate development of hardware and software. Now, in most modern architecture, we get programmable SOCs, okay, containerized apps. We get to move to that. It's very important. The app is everything it needs to run on these unified frameworks. Both require real-time processing, millisecond response times, deterministic behavior. Okay. And they both have their own safety standards. Okay, these things they all have in common. 26262 is technically an offshoot of 61508, some added safety and development rules and regulations. So these are shared and parallel changes in industrial and in automotive, being driven by shared drivers. They're driven by the same things. Why do we have separate design cycles and environments and systems for them? If it is fast, safe, and secure enough for automotive, where can't you put it? Okay, what is acceptably unsafe for your non-automotive application? If it's cost prohibitive, then it's cost prohibitive, and you deal with that. But if you build in the cost of separate design channels for your industrial design and your automotive design, how does that affect your overall cost? If you're talking about a centralized compute for automotive, could that not also design, an industrial robot, an embedded PC, machine control? There's all sorts of areas inside industrial. At the same time, as we talk about the spread from automotive to industrial, and as an automotive guy, that's the way I naturally think about it. Auto can learn a lot from IoT, but don't tell them I said that. There's also lower barriers for entry to automotive than there ever have been, not since the 1920s. In 100 years, it's never been easier to enter the automotive space than it is now. Some of these org charts are being torn up. They're being torn up through JVs. They're being torn up through offshoots. People are setting up their own small company and saying, what can you do if you don't have the tyranny of this org chart behind you? What can you do if you start from first principles? And one of those should be, why are we designing the way we always have done? Why are we designing for an analog world in a digital environment? If you are Tesla, if you are Rivian, if you are Lucid, if you are Xiaomi Automotive, or if you're BYD, you are acting this way. You are acting, as a tech startup rather than a car company. What is that advantage? How do we put it in two words? They're two words that are very familiar to everyone in this room. They have a flexible, scalable advantage in this space. Okay? There is more resemblance now to traditional compute. We talk about these lower barriers. Is it that the new compute is going into automotive? It's not 8 or 16-bit MCUs. Okay? It's not the very custom ECUs that are specific sometimes to a particular make and a particular model of car. It looks more like an industrial PC, an embedded PC, a server to some extent. I kind of wonder if there's general convergence on a few types of compute. We probably can identify sort of archetypes of compute. When in doubt, move closer to one of these poles. I talk about a rhombus of compute, where you see that lower-powered apps processors have much more in common with higher-performance MCUs than they do with high-powered apps processors. The same with MCUs and very, very low-power MCUs. But if there's space in between, is there value in splitting that space, and how should we look at it? Probably another talk for another time. This does solve some supply chain issues. It's not going to fix everything for you, but it does potentially solve some volume issues. You're producing more volume, fewer SKUs. Your foundries are going to thank you. If you can put that software on anything, the software developer is going to thank you. Say, you have this performance capability. We can make use of that. And if you say to the industrial tech people, hey, you can define your manufacturing technology through software, and the dream obviously is that you can retool at a keyboard from an air-conditioned office between shifts. So what we're talking about is changing to a more agile compute overall. RISC-V will be found everywhere there is agile compute. Okay? Because again, flexible, scalable, safe, and secure. We've done a tremendous job inside this community in focusing on safety and security and being an ISA that was born in a secure age, in a security-conscious age, looking at safety features from day one. And that's going to be incredibly important. The sense of independence as well. I mean, the car makers, the industrial people, they want to make sure that they have control over their own destiny, that they are not beholden to a license, to a geopolitical issue, to all these things that can affect where and how they deploy their IP. They want to be in control of that. Right-sizing intelligence, which is something, so you want to have the right amount of compute in the car. You just don't throw endless amounts into it and say, well, just make sure that's enough. You want to be able to offload and have that sort of that flexible, scalable intelligence in there that you can use when you need it. If you're moving stuff to the edge, do it on the edge, but do it for good reasons, right? Do the stuff in the cloud that's meant to do in the cloud. Powerful enough controllers that can offload, that can balance things in a software-defined system. You've got 4 or 6. You shift stuff around when you need to. You put it in the cloud if you need to put it in the cloud. You make a system that's more than the sum of controllers. Right? 6 controllers, you can balance stuff around. That gives you a lot of flexibility and a lot of capability. And industrial needs this same capabilities. It's not just an automotive-only issue. Industrial needs this too. Looking at regions. Okay. So where it's all kicking off, China is particularly the locus of SDV. If we look at those OEMs, on the 51% of the OEMs that are in the top 10 are China-based. I think that's, that's a pretty startling statistic. If we look, Tesla's in there too, but I think it's not controversial for me to say that Tesla is weird. I'm not saying they're good or bad. I'm saying that they're different from all the other Western OEMs, in this regard. If we look at industrial automation, again, we see like the largest volumes by far are going to be found in APAC. And RISC-V, again, we see most RISC-V shipments coming from China. And I originally thought that this was my last slide. And then I thought about it a little bit more. I don't think the story here is actually just China. I think EMEA has a huge story to tell. If we look at revenue coming from industrial automation, an outsized share of that revenue is coming from EMEA, even on lower volumes, which means that the higher performance stuff is coming from there. Okay, the volumes again on RISC-V, EMEA is hitting above its weight on this. And again, that's in the higher performance stuff that's coming from these European companies. If it's the European car makers, they're doing very well. Again, Volkswagen, BMW investing hugely in software-defined vehicles. Volvo, with that Chinese influence, heavily invested in software-defined vehicles. So I think Europe has a huge story to tell here. What's really interesting is the comparison between Europe and Japan. Japan was behind on SDV, investing in it heavily and catching up. Japan, again, investing heavily in industrial automation. Europe and Japan's industrial bases are only going to be revived through automation, through computers, through digitalization. I think there's a lot in common between those two. I think that is the best comparison that we can make. So that, and again, I think it's a huge opportunity for RISC-V and all of this, because where they both need flexible, agile compute. And I think that's a huge story that we can be telling as far as getting automation, getting SDV going in both of these areas. North America, nothing against you. You're just not as interesting to me right now. I'll catch you on the next time. That is what I came to talk about today. I think we should be looking at automotive and industrial development as a type of safe, secure, connected, embedded, intelligent device. Okay, when you have a certified, safe, software-defined system, it's not easy to say. Do you need to define it beyond that? Do you need to have a little stylized line drawing of a car on it to make everyone feel better? What meaning is there in that distinction? Look at how we can get more out of our development resources that way. Think how we can use that to create more powerful, flexible solutions across the board. Okay? Thank you very much.
Thanks a lot.